All right, welcome back to The Explainer. Today, we're tackling the final, absolutely critical piece of our subsea architecture module. We've spent a ton of time looking at these incredible, highly complex pieces of engineering, the wellheads, subsea trees, manifolds, those massive control umbilicals. But here's the real challenge. How do we actually guarantee that all these intricate pieces work together when they're finally deployed thousands of feet underwater? Well, that is exactly what we're going to master right now.
So let me pose a question to you. What do you think is the single biggest cause of offshore delay? Imagine a multi-billion-dollar deepwater project. Every individual component is perfectly engineered. The subsea tree? Flawless. The drilling rig is state-of-the-art. The platform hull is a literal marvel of modern design. And yet, this project can still blow its schedule by months, bleeding capital every single day. Why? What goes wrong when the engineering of the individual parts is absolutely perfect?
The answer isn't a broken part, it's a mismatched interface. It happens because the drilling team, the hull team, and the subsea team all design their flawless pieces just slightly out of sync with one another. Because honestly, when no single engineer or team sees the entire system across every boundary at once, things just slip through the cracks.
To really understand why this is so catastrophic in our industry, we have to look back at our core operating reality. Think back to 1947. A well was completed in 15 feet of water off the coast of Louisiana. If something didn't quite fit, a guy could literally stand next to it in the water and just fix it. Today, we're completing wells in waters so incredibly deep, the pressure would crush a car. Nobody walks down there anymore to tighten a bolt or force a connection. Every single thing has to happen through a machine, usually an ROV, on the very first try. Total inaccessibility means perfect coordination isn't just a nice-to-have, it's a non-negotiable mandate. And that brings us to the discipline that prevents these disasters. Section 1. The connective tissue. I love this analogy metaphor because it just hits the nail on the head. You can have the most perfectly formed individual engineering bones, the drilling system, the hull, the subsea stack, but without tendons linking every single joint at precisely the right points, nothing moves as one functioning body. Interface management is that connective tissue. Its entire job is to coordinate all those specialist deliverables so they actually physically and functionally fit together, catching mismatches in dimensions, timing, data, or assumptions before they ever leave dry land. To pull this off, we use something called an Interface Control Document, or ICD. Think of an ICD like a piece in a giant jigsaw puzzle. It locks together exactly what one team delivers with exactly what the receiving team requires at that specific boundary. Whether it's a physical connection, like how a riser attaches to the hull, or digital output data passing from the drilling team to the subsea team, the ICD creates a formal, rigorous record. It ensures output perfectly matches input. Section 2. Managing unstated assumptions. Now, what's really fascinating is why these interfaces fail in the first place. I mean, on paper, it sounds pretty simple to just match things up, right? But interfaces are incredibly dangerous because they are the exact locations where unstated implicit assumptions live. Take this classic scenario. The hull engineering team goes to work assuming a specific range of riser tension. Meanwhile, halfway across the world, the subsea team designs their equipment assuming a specific motion envelope from the host platform. Both teams are doing phenomenal work based on their assumptions. But if those assumptions diverge and are never explicitly reconciled on paper using an ICD, well, they remain hidden. And they'll surface for the very first time, expensively, in the water during installation. It's literally like a track and field relay race. You could put together a team of 4 runners who are individually the fastest on the planet. But if they haven't practiced the baton handoff, they're going to lose the race. Having the fastest independent drilling, hull, and subsea teams is completely useless if nobody practiced the handoff. Section 3. The hidden interface risk. I want to test your intuition here on where the greatest project risks actually hide. Which of these 2 types of interfaces do you think poses the most dangerous hidden risk to a massive offshore project? Is it the highly complex, multi-system interfaces, or the simple, everyday interfaces? It might surprise you, but the answer is for sure the simple interfaces. Highly complex interfaces get intense scrutiny by default. Everyone knows they're risky, so they get documented to death. But the simple-looking interfaces, they often just get skipped in the formal ICD paperwork because they seem so obvious. And because they seem obvious, fatal assumption mismatches sneak right through undetected, just waiting to completely derail the project on installation day. Section 4. The 3 quality gates. So how do we actually catch these mismatches before they hit the seabed? In subsea engineering, we rely on a mandatory sequence of testing to prove the whole shebang works before it ever touches seawater. We walk the hardware through 3 chronological locking gates. First up is the FAT, the Factory Acceptance Test. This happens right at the manufacturer's bench to verify a single component works, like a valve or a connector. Next is the EFAT, the Extended FAT. This tests integrated subassemblies together, proving that the components actually talk to each other correctly before they leave the shop. And finally, the Ultimate Defensive Shield, the SIT, or System Integration Test. This is a full-scale simulation of the actual installation sequence, done on the quad side using real ROV tooling, all before anything gets mobilized offshore.
Listen, I cannot emphasize this enough. Skipping or compressing that final system integration test is one of the most common and absolutely devastating root causes of offshore delay. Bypassing the SIT to save a little time upfront means you're almost guaranteed to find your interface problems on the quay side, where fixed cost stays, or far worse, you find them subsea, and that shifts us into entirely different financial stakes. Which brings us to Section 5, Economics of Subsea Delays. Let's look at the brutal math behind deep water interventions so we can truly appreciate why this rigorous paperwork and testing is absolutely critical. A diesel-powered diving vessel in shallow water, that might cost tens of thousands of dollars a day. But a deep-water ROV support vessel required to fix a single subsea fault, that spread rate can easily run anywhere from $150,000 to $300,000 per day. Let that sink in, and that's before you even calculate the massive cost of lost oil production. When you look at those numbers, it becomes instantly clear why a paperwork fix early on is astronomically cheaper than a vessel day fix later. The cost and the time required to resolve a mismatched interface scales exponentially the further down the timeline it goes undetected. A subtle dimensional mismatch, caught on paper months before fabrication, is literally a low-cost email. That same mismatch caught during the quayside SIT, that costs days of grinding and rewelding. If it goes completely undetected and makes it all the way to the subsea installation phase, that mistake costs weeks of schedule and tens of millions of dollars in vessel spread rates.
So to wrap this up, documenting these boundaries isn't just about keeping organized files. Interface management is not a coordination nicety, it is risk management in disguise. Every unmanaged interface is a hidden project risk just sitting there quietly until physics forces it into the open. Rigorous ICDs and thorough system integration testing are literally the only reliable methods to prevent these hidden risks from destroying a project's economics. And with that, we've successfully closed out our first major module. You now understand the full architecture of a subsea field, from the wellhead to the host and the connective tissue that holds the whole thing together. But knowing how to build it leads us to our next massive challenge. You've built the perfect subsea architecture, but can the fluid actually flow through it reliably without freezing or clogging for the next 20 years? That is the high-stakes world of flow assurance, and we are going to dive deep into that in Module 2. I'll see you there.